Okay, so let's do a quick recap of liquids. It's important to remember that liquids have a definite volume, which means the volume does not change. It has an indefinite shape, which means the shape can change, and it's low compressibility. So it resists being compressed. Now, there are some terms we're going to use when we talk about liquids. The first is surface tension. Surface tension is the resistance of a liquid to increase its surface area. So when liquids bead up on themselves, that's because of surface tension. All of the molecules are pulling in on each other. Now, when we have large intermolecular forces, we're going to have high surface tension. Remember, our intermolecular forces, we've got three types: dipole-dipole, LDF, and hydrogen bonding. So the higher the intermolecular forces, the higher the surface tension. Capillary action is the spontaneous rising of a liquid in a narrow tube. So if you put a straw in just a little bit of water, you'd see that water climb up the straw. Now, this happens if we have a polar liquid and a polar tube, or a nonpolar liquid and a nonpolar tube, but they both have to have the same type of material, okay? So cohesive forces are intermolecular forces between a liquid's molecule versus adhesive forces are the forces between the liquid and the container. Now, when we talk about adhesive forces, remember when we're measuring the volume of a liquid, the liquid in our tube isn't going to be straight across, it's going to go up. We called this a meniscus. It's climbing the sides of the graduated cylinder because of those adhesive forces, okay? So the next term we need to know about is viscosity, and it's a measure of a liquid's resistance to flow. So think about something like water versus syrup. If I pour water on a table, it's going to spread out, not very viscous. If I pour syrup on the table, it's going to spread very, very slowly. It's very viscous, okay? If we have large intermolecular forces, we have high viscosity. Now, intermolecular forces don't just affect viscosity and surface tension, they also affect boiling point. The bigger the intermolecular forces, the higher the boiling point. Now we've got this table below, and if we look at these molecules, H2O and H2S are basically the same shape of molecule. Sulfur is actually a bigger atom than oxygen, but H2O has a much, much, much higher boiling point than H2S. The reason is because of intermolecular forces. H2O has London dispersion, LDF, but so does H2S, and H2S would have bigger LDF because S is bigger. However, they both have dipole-dipole as well because they're both going to be polar, but only H2O is going to be capable of hydrogen bonding. Because it's capable of hydrogen bonding, its intermolecular forces are much, much higher than H2S, and so its boiling point is much, much higher. Same thing when we look at HF versus HCl. Cl is a bigger atom than F, but because HF is capable of hydrogen bonding, it's going to have the highest intermolecular forces and the highest boiling point. So this is what we need to know about liquids. When we talk about solids, we're going to have two big categories of solids. We can have crystalline solids, which are going to have regular arrangements of atoms or molecules, and amorphous solids, which are going to have disordered arrangements of atoms or molecules. Now, glass is the big one that they usually mention for amorphous solids. When we talk about crystalline, usually everybody's lined up, everybody's neat, everybody's orderly. But in an amorphous solid, you're going to have this random arrangement, and it's not going to be neat and orderly. Okay? Now, when we talk about our crystalline solids, you'll hear us talk about a lattice, a crystal lattice. That's the 3D structure. And we'll talk about a unit cell, which is the smallest repeating unit. So when we talked about molecules, the smallest molecule of water is H2O. When we talk about ionic compounds, we're going to simplify our ratios. So here's the example here. I've got SN2CO3 4, tin 4 carbonate. Now if I look at these 2 and 4, I can simplify them to 1 and 2. The reason we simplify ionic compounds is we don't really have molecules. We've got this big repeating crystalline structure. And so we just say that the lowest whole number ratio is going to be our compound. Okay? Now when we talk about an ionic compound, remember ionic compounds are going to have metals, which form a cation, a positively charged ion. It's going to have a nonmetal, which is going to form a negatively charged anion. Ionic compounds are going to have very high melting points and boiling points, and the reason is because of these very strong bonds. Coulomb's law, which is spelled wrong there should be a U here. Coulomb's law is what determines how strong an ionic bond is. The Q's represented the ionic charge. D is the distance between the ions. So, if we have small ions with big charges, we're going to have very, very strong ionic bonds, and they're going to hold very tightly together, and we're going to have a very, very high melting point. Now, ionic compounds conduct electricity, but they only conduct electricity when they're dissolved in water or if we melt them. Now, because they can conduct electricity, sometimes you'll see the word used electrolyte. Like in Gatorade commercials, they say there are electrolytes. That means that there are ions in your solution. Okay? So ionic compounds are metals and nonmetals. Molecular solids are nonmetals only. Ionic compounds have ionic bonds. Molecular compounds have covalent bonds. Ionic compounds, somebody's gaining an electron, somebody's losing an electron. Molecular solids, they're sharing electrons. Now, because they are sharing, the bond isn't nearly as strong as an ionic solid, so they're going to have lower melting points. They also are not going to conduct electricity. Okay? Now, when we talk about atomic solids, atomic as in atoms, only have a single type of element. So for example, we'll have carbon, or we'll just have lead, or we'll just have gold, but it's only one type of atom. When we talk about atomic solids, sometimes we'll describe them as allotropes. We have two or more different forms of the same element. So carbon can exist as elemental carbon as a diamond. Carbon can exist as elemental carbon as graphite. And they look very, very different from each other, different melting points, boiling points, freezing points, different properties, colors, textures. But they're both elemental carbon. Okay? Now, when we talk about atomic solids, we can have metallic solids, which, as the name implies, are made up of metals. In metals, we've got delocalized, non-directional covalent bonding. So when we have our metals, basically think of the electrons as just moving wherever they want around our center atom. That's what delocalized means. And so we've got bonding, but unlike our other bonding where we actually said it's got angles and we can tell the directions, in metallic solids, we're not going to have these. We can have network solids, which will have directional covalent bonding, like we've talked about before. But a network solid is going to be a little bit different because we're going to form giant molecules. So it's going to go on and on and on and on and on. We can also have group 8A solids. Group 8A solids, as the name implies, group 8, are only noble gas. Now when they form, what's going to happen is we're going to have London dispersion forces, or LDF, because again, remember they don't need to share electrons really to form, but we can have those electrons move around and get partially positive sides and partially negative sides, in which case they'll come together. Now this table below describes the differences between our types of solids. This is super important. I would take some time and make sure I make flashcards or do descriptions or notes or something so that I start studying these so that I can tell them apart. Okay? It's going to be important for you to know the difference between a molecular compound, an ionic compound, a metallic compound, all of those things.